Hello everyone. In this video, we'll try to explain how the resistance and area as well as the length of a conductor are related to each other. Right. So to help us understand that, we'll have a small diagram through which we'll try to understand the relationship between resistance and area and length. Right. So let's consider this tube. Right. Let's consider the cross-sectional area of this tube is A and the length as L1. Now let's give a small pressure, or let's pull the tubes on the both the sides. So what will happen is now the tube's length will increase. Right. So the tube's length increases. As a result, the area, let's name it E2, will decrease. This has higher area, this has lower area. At the same time, if you look at the length, the L1 has increased and we have got new length which is L2. Okay, now comes the very important part. Let's say in this tube we are letting water flow. So what happens is, if the water flow is like this, the water will flow smoothly. Similarly, if you put the same water flow, what will happen? Here it will get affected, again affected, again affected, right? So this will produce more resistance, right? So we can say that if the area is high, then the resistance will be low, right? So which can also be written as area is proportional or inversely proportional to 1 by r. Whereas if you see here, the length here is less, right? So when the length increases, what happens? The resistance also increases. So we can write that area is proportional to length. Sorry, forgive me. Not area, the resistance is proportional to length. So taking this together, I can write resistance is proportional to length and inversely proportional to area. But this proportionality, we are going to replace that proportionality using a constant which is the new equation now becomes rho into L divided by A, right, where rho is resistivity, right? So now hope you would have understood this formula. R is rho into L by A. Okay, so this is just the resistance, right? What we have done is, we had a tube like this and the tube has been pushed, so the length increases and the resistance varies. But this is just a single resistance. When you consider the variation in resistance, that is a change, what we have to do is we'll have to take differentiation. So here I'm going to differentiate this equation. So for our convenience, I'm going to rename this equation as equation number 1. Now I'm going to take differentiation for this equation, right? So what I'll get is, see, all these are individual constants, variables, right? So I'm going to consider them as individual, and I'm going to take the differentiation with respect to strain, right? Strain is the force that pulled the tube, right? So dr by ds is equal to, right, first I'm going to consider rho, right? So if I consider rho, L and A will be constants. What happens? D rho by ds, then plus, then comes the next component L. So rho by A dl by ds. Now let's move to the next component A. So A is in the bottom, so if we take differentiation, what will happen is A will become, let's just equal to minus something like this, right? So what I'm going to do here is in this equation minus, because of this here it's minus 2, whereas in our case it should be a minus 2. Instead of doing that, I'm going to write a 1 by a square into dA by ds into the constants, which is rho by, I'm sorry, we cannot write a, forgive me, we cannot write a because a is what we divided, so it must be rho into, right? So remember this equation. I'm going to write the same equation as here. dr by ds is equal to rho into dl divided by a into ds minus rho l by a square into dA by ds plus l into d rho by a into ds. So what I'm going to do is I'm going to rename this equation as equation number 2. Now comes the next part, in which we will be dividing equation number 2 by 1. This will help us the exact change, the variation that has happened, right? Okay, so if we divide 2 by 1, what will happen? See, look at this equation. We know this equation, right? R is equal to rho L by A, right? For our convenience, let me write that here. R is equal to rho L by A, right? So now we are going to divide equation number 2 by 1. So if I divide it, 1 by R into dr by ds is equal to rho into dl by a into ds into, we are dividing, so this a by rho l, right? Dividing means this will go to the down, this will go to the up, right? That is what happens if we divide, right? Okay, I did the same, right? So this 2 will get cancelled, this 2 will get cancelled, right? So we completed the first one. Now write the second one, minus rho l by a square into dA by ds into a by rho l. So rho l will get cancelled, a square 1a will get cancelled, right? So we'll have just a, right? Now plus l into d rho by a into ds into a by rho l. This l and l will get cancelled, this will be left, right? So what I can write from this is that 1 by r into dr by ds is equal to 1 by l dl by ds minus 1 by a into dA by ds plus 1 by rho into d rho by ds. Right, here an important thing that you have to look at the numerator and the remainder. Okay, let me take orange color to help you identify this. dr by r. dr is change in resistance, r is resistance. The change in resistance with respect to resistance. Similarly, look at this, change in length with respect to length, change in area with respect to area, change in resistivity with respect to resistivity, right? So what I can write is that instead of dr by r, I can also write del r by r. Del again is change, displacement, right? Is equal to del l by l minus del a by a plus del rho by rho. Okay, so but I cannot exactly rewrite this, but instead of this I can use this, and okay, instead of this I can use this, instead of this I can use this, instead of this I can use this. right? Both are interchangeable, right? So let's rename this as equation number 3. Now moving to the next part, right? So now here we are dealing with a circle, right? It's a tube, so it's like a conductor which has cross-sectional area at both the ends, right? So considering that cross-sectional area, we're going to talk about area, which is here is like a circle, so pi or square. But we know diameter is equal to 2 into r, so I'm going to use that here. So what will I get? Pi into d by 2 the whole square, which will be pi d square the whole divided by 4, right? So remember this. Let's put down this equation as equation number 4. Now let's use this equation number 4. Let's differentiate this equation number 4 with respect to s. Differentiating equation number 4 with respect to s. So if I do this, what will happen is, see, this is what we are going to differentiate. So 1 by a into dA by ds is equal to this part. Okay, so first if you differentiate d square, let's say 2 into pi d by 4 the whole divided by the whole component, which is pi by 4 into d square, since we are did dd by ds, right? So we can cancel out pi and pi, 4 and this, they cannot be cancelled, sorry, 4 and 4 can be cancelled, 1d and d can be cancelled. So thus 1 by a into dA by ds can be written as 2 by d into dd by ds. I'm going to name this equation as equation number 5. Okay, so now what I'm going to do is, look at this equation carefully. I'm going to use this equation in equation number 3. We got this equation, right? Okay, I made a mistake. This is our equation number 3, right? So in this equation, I'm trying to use this part, dd by dds is here, right? We have dd by ds, no dd by ds. Do we have dA by ds? Yes, we have dA by ds, right? So here we have dA by ds. This we are going to replace with the equation that we have got here, right? So substitute equation 5 in 3. So if I do it, what will I get is 1 by r into dr by ds is equal to 1 by l dl by ds minus 2 by d dd by ds, right? So this is the term which we have changed, right? So to help you understand that, I'm highlighting with another color, then plus the term which is same as that in your equation number 3, b, that should be rho, d by d. Yes, I'm going to give this equation a name as sets. Now comes a very important part which you should definitely know. What is that? There is a ratio which says that when you pull an object, let's say this is the object, you are pulling this object on both the sides. So what happens is that the length will change, likewise the area will change. So the change of length is like this, right? So from right to left, whereas the change of area will be from top to bottom, right? So there is something called as Poisson's ratio. Poisson's ratio is this divided by this, that is change in the diameter divided by change in length. You can say this by this in symbol, or you can say change in dia divided by change in length, right? So the same thing I'm going to write, the same thing can also be written as minus of dd by d the whole divided by dl by l. I'm going to rename this equation as equation number 7. Another important feature that you have, another important thing that you have to notice, that this Poisson ratio is denoted using a symbol mu. So mu is equal to minus dd by d divided by dl by l. So what I'm going to do is rewrite the equation number 7 so that it can match with the equation number 6. So you look at the sets, we have dd by d here. Try to highlight. We have this dd by d here, right? So to match that, I'm rewriting this equation number 7. Rewriting equation number 7 as dou d by, forgive me, that is dd by d is equal to minus of mu into dl by l. This I'm going to write as equation number 8. Now what I'm going to do is very simple. I'm going to substitute equation number 8 in equation number 6. Let's go back and see what is equation number 6. This one, the one where you put this equation, that is the differentiation, and after differentiating we divided and we got an equation, right? That is equation number 6. That in that equation we are going to substitute, and we will get a new derivation, which is 1 by r into dr by ds is equal to 1 by l dl by ds plus, okay, so this is the point, this is where the equation changes. Earlier the equation there was minus, right? So look, it is minus here, but now in place of dd by d we are substituting what? In place of dd at d we are substituting minus mu into dl, right? So the equation now becomes plus 2. The reason we have 2 is because we have 2 here, right? So saying 2, then dl into mu divided by l into ds plus, same as the previous equation, 1 by rho into d rho by ds. I'm going to name this equation as equation number 9, right? So another thing now we have to notice is that now that we have this equation is like a very specific one, but for a minute values or for small variations, very small variation, we can rewrite this equation as, look at this del r by r can be written as, dr by r can be written as del r by r, as I told previously. And similarly here del l by l, similarly here del l by l, but we have 2 and mu, so 2 mu del l by l, and plus del rho by rho, right? So this is equation number 10. This is your final equation which will tell you the relationship between a resistor and length, resistor and resistivity of a conductor, right? So this is the basics behind the strain gauge, how a resistance will change the length and area. That is length and area here, this length and this length in sense, if you say this resistivity, these two terms are like something related to the something related to changes, right? Something that represents a displacement. Whereas if you take this thing, this is electrical, right? So displacement is related to electrical activity. This is the equation beyond it, right? So now we have to know another important concept, very important concept, which is gauge factor, right? I can say here one write it as a gauge factor, or in certain cases people write it as GAG, gauge factor, whatever it is. So gauge factor, we are going to represent gauge factor as the change in resistance per change in length. So I'm going to name this equation 11, and I'm going to rewrite the same equation as del R by R is equal to GF into del L by L. So this del L by L, let's see. Okay, so here I said this equation, right? I said this, right? Length, the change in length, which is it moves from left and right, it is expanding. So we call this as strain, right? So instead of writing del L by L, I can write it as strain, which is del L by L, which is strain, right? So that is what I'm going to use here. So my del R by R is equal to GF into epsilon. This will be my equation number 12. Now substitute 12 in equation number 10. Equation number 10 is the one that we derived here, right? This is equation number 10. If I substitute here, what am I going to substitute? Del R by R. So del R by R, I'm going to substitute here. So if I substitute, what will be this? GF will be equal to 1 plus 2V plus del R by, del rho by rho, the whole divided by epsilon, right? So let's mark it as equation number 13, right? So another thing that you have to notice that if the change in the value of resistivity due to strain is almost negligible, what we're talking is, if the resistivity, that is the rho, is very low, that it is negligible, then we can neglect it. So if I neglect that, then my equation number 13 would become like this, which is GF is equal to 1 plus 2, right? So this is how you find gauge factor. I hope this would have explained you, or this small video would have helped you understanding how we got this equation. I'd go through this video once again, and while listening to the video, pause whenever necessary and write this video down. Write this derivations down so that you can understand easily, right? Okay, thank you.